question then.
Who are the type of cats? Like a larger umbrella of wild cats?
So today is a review day. This can be somewhat flexible, free form. I'll start going over what we covered. I will have to abbreviate a lot of things. It's a whole semester. Try and point out things that you really should know for the exam. But you are welcome to stop me, ask questions, throw problems at me from the homework if you wish, whatever you want. I think there'll be plenty of time to go through everything. I guess I should say the obvious, you can use a calculator. I'll bring some calculators if you don't have one. Usually you get a cheat sheet, so you can put some hard to remember formulas or derivatives or whatever. The midterm, I actually kind of enhanced that on the first page. I put a lot of stuff. I'm not doing that on the final, so make sure anything you feel like you would need that will help remembering to write it down. All right. Yeah. There are a lot of papers to hand back. If, for some reason, you handed in a piece of homework and you have not gotten it back, please let me know. I think I mentioned the grader seems to not be as focused this semester. In addition, if there's anything that is not listed in the grades that you think you turned in, please send me an email telling me. All right. Any questions before I start running? Yes?
Is the cheat sheet that we can bring double-sided?
Yes.
Okay.
2 sides. And you don't have to turn it in. All right. I'm going to start. We're going to talk about limits. But I'm going to do things in a little different order. You recall there's this idea of continuity. And the touchy-feely idea behind continuity is it's a function that you can draw without taking your pen off the paper. It's a good heuristic. It's not 100% correct all the time, but there's a definition, which is that the limit as x approaches some value of the function equal to the function at that value. This defines a continuous function at the point A, and of course if this is true everywhere, then the function is continuous everywhere. It could be continuous on an interval. So I mention this because there's a great number of functions we know are continuous. And that means if we want to evaluate the limit of that function, we just have to plug it in. This isn't true. We're going to cover where that's not true, but as examples, polynomial functions, they're all continuous everywhere. The trig functions, sine and cosine, are continuous everywhere. tangent and the other four functions are continuous on their domain. So, for example, tangent, I go like this. It's undefined at certain points, like here, pi over 2, but everywhere else it's continuous. Exponential functions, log functions, they're all continuous. Same thing with hyperbolics, they're continuous on their domain. So any function which is continuous, if I ask you, what's the limit at some point, you just plug it in. So clearly, if we have a limit that's not going to be something you can just plug in, we have to look a little deeper. That would be at a point where it's not defined. So just as an example, take a look at the limit x squared plus x plus 2, x plus 1 as x goes to minus 1. So here we have denominator has become 0 and the numerator becomes 0. So we've learned two strategies for dealing with this kind of limit. In a simple case like this, we might be able to factor and using our limit laws, we know the limit of a product is the product of the limits. Well, the limit of x plus 1 over x plus 1 is going to be 1. So now the limit here is going to be the limit of x plus 2, which is going to be 1. The other strategy is if we're heading towards an indeterminate form, like here, 0 over 0, we can apply L'Hopital's rule. L'Hopital's rule says we have a limit x approaches a of x over g of x, and f of x over g of x approaches some indeterminate form, then this will be equal to the limit as x approaches a of f prime of x over g prime of x. Likewise, if this is approaching an indeterminate form, you can find the derivative again if you needed to. All right, so I think I can come up with some problems, but that's really all I'm going to say about limits. I want to say a little more about continuity, or rather discontinuity. Recall that if a function is not continuous at a point, there are various ways that could be the case. One way is you have a function, and at some point you just happen to have a hole there. It's not defined there. This is called a removable discontinuity, because we could just define the function to be the value at the limit here, and then it would be continuous at that point. We have a jump discontinuity where the function just jumps from one place to another, and that's clearly not removable. And you might have asymptote and a function that goes off to infinity. So we would say it's discontinuous at infinity. If I ask for the limit as we approach this, it gets at least from in my diagram from the left. On the left, it's infinity. All right. Okay. Any questions? No, it's kind of a neurotic compulsion. I hate ending the semester with papers in my session. I feel like I have to hold on to them. So, if I can, I'm going to get rid of them. All right. For anybody who came in after I started, you're free to stop me, ask questions, give me problems to do, or ask me to make something up. Okay, you should definitely know the definition, the formula for a derivative. Derivative of a function is the limit h approaches 0. The function of x plus h minus function of x over h. This is when we're starting from scratch, we put a function in here and we find out its derivative. You should also recognize this pattern. If I were to write down something like, what's the limit as h approaches 0 of sine of x plus h minus sine of x over h, you look at that and go, well, wait a minute. That's the definition of the derivative of the sine of x. So I don't have to. I have to go through the complicated derivation of this. I know that the derivative of sine is the cosine. So that's something you should be aware of. I think we had a problem like that on one of the midterms. You should be familiar with this syntax. This is the Newtonian syntax, more or less. The second derivative would be 2 quote marks and so forth. After 3, you don't really have to know this at this point, but you put a Roman numeral here. So this is like the 4th derivative of f of x. You should also know how to write this with the Leibniz notation. We would say d dx of a function is the derivative. Second derivative, we kind of use this tortured syntax. Nothing being squared here, but this means we apply the derivative to this function twice. I apologize, I'm confused here. Are you Italian?
I'm Italian.
Okay, because my brain didn't look like that. But you're sitting in the seats.
Yeah.
Okay. All right. You certainly should know the basic derivatives. Either in art or jot them down. Derivative of a constant is 0, derivative of x to the n, use the power rule. Hope I got that right. Of course, the derivative of just x would be 1. The trig functions, sine and cosine, derivative of the cosine, negative sine, and secant squared. I think I'm going to go one more step. Probably should know that the derivative of the secant is secant times the tangent. You should absolutely know, especially if you're going on in engineering or any of the sciences, anything where you might end up in a differential equations class, you need to know that the derivative of e to the x is e to the x. Kind of less important. If you have some other base, a to the x, it's a to the x, but times a factor log of a. So these are some basic derivatives you should know, should be able to apply. We also have a number of rules that can help us find a derivative of a more complicated function. Most basic would be the sum rule. Derivative of the sum is the sum of the derivatives.
Which is derivative of cosine, I think with the wrong value.
Oh, yeah, I wrote the wrong value. Thank you. Negative sign. Is that what you meant? Thank you. Some of these rules we're going to see work in reverse too, right? We're going to find the integral of this, integral of this, or vice versa. The product rule. It's not the derivative of f times the derivative of g. Make sure you don't make that mistake. It is nice and symmetric though. Know that by now. I advise you to put in your cheat sheet the quotient rule. And every time I come back to it, I have to, I can remember it, but I often get the sign wrong. What comes first? It's the derivative of f times g times the derivative of g times f over g squared. You know that. Probably the most difficult one, and maybe we should do some problems with it. The chain rule says that derivative of f of g of x, a composition of functions, can be found as derivative of f at g of x times g prime of x. Or in the Leibniz notation, which sometimes is more convenient, dy dx equals dy du dx, where the connection here is we're calling u g of x, and y as functions. I don't know. Say, we'll just do a simple example, sine of x squared plus x. We want to find the derivative, so we think of sine as f, x squared plus x is g. So the derivative of f at g, the derivative of the sine is the cosine at g, well that's x squared plus x, and then we have to multiply by g prime. So the derivative of x squared plus x is 2x plus 1. Now, if this were a function, we could just repeat. And that's why we call it chain rule. Have like cosine of x cubed in here or something. And then we have to just keep multiplying it out. Okay. This song will get tired of this. So we'll just refer to this abstractly first, and we'll do a real example. If I give you some function and some point on the function, I say, I want to know what the equation of the line, the tangent line to this function is at this point. How do I go about it? Well, first thing I'm going to do is find the derivative. I'm going to evaluate it at that point. And that brings us back to our Algebra 1 class in high school. This is the slope m. And from there, it's pretty easy just to apply the slope point form. Y minus y0 equals m times x minus x0. You get that equation. You should be able to do that in your sleep, maybe. Okay, so here's a situation where that would come in handy. Say I have a function x squared plus y squared is xy. I didn't do my due diligence to figure out a good point on here. We'll try 0, 0 and see if that might be undefined, which wouldn't be good, but we'll try it anyway. So here now, I don't have an explicit function. So I have to do implicit differentiation. I'm thinking of this as x squared plus some function y of x squared equals x times that function y. And I just go ahead and find the derivative of both sides. So here, with respect to x, here this is 2x. Derivative of y squared is going to be 2y of x times the derivative of y. That's the chain rule. On this side, I'm going to have to use the product rule, x times derivative of y plus y times derivative of x plus 1. And I look back at this equation and I see, oh, I have the derivative of y twice. So I want to collect those. 2 side, and we put y of x minus 2x on this side. You don't have to keep writing called x. It's much simpler to just kind of skip that, but all right. I factor out y prime, y minus x equals y of x minus 2x, and now I divide through by 2y minus x, and I have an implicit formula for the derivative. So y of x minus 2x over 2y minus x. Yeah, I need a better point in this. This is going to be undefined. But if I give you a point on this curve, you can just plug x and y in here and get m, and then use the formula for the line. So you should know how to find the tangent line, equation of a tangent line. You should be able to do implicit differentiation. Catching my breath. I think it's because we're way up hill. I don't think the oxygen level is that much less than down in the valleys. Okay, so let's talk a minute about what a related rates problem is, because that tends to catch a lot of people. When I talk about rate, it doesn't have to be, but usually we're talking about some kind of motion or function with respect to time. So, some f of t. And we don't know, we want to know, something about f of t. I'm going to write df dt. But maybe we know something with respect to u dt. Well, we look at this and we think about the chain rule. We can find df du, and one of these, then we can find the other. So what would that look like? We saw a few different problems. One of them kind of looked like this. It's the falling ladder problem. So the end of the ladder is falling down at some constant rate. Actually, if there are any physics majors here, or anybody's going to take physics, you know that the ladder isn't going to fall at a constant rate. Gravity's pulling it, it's going to accelerate, but we're just going to keep it simple. So this is my y here. So we start off knowing dy dt. And we want to know how fast is, we assume this is frictionless, and we want to know how fast this side of the ladder is moving out. That's dx dt. So what we're missing here is the relationship between x and y. We knew dy dx. Oh, there's our chain rule. So let's just throw some numbers here. dy dt is negative 5 feet per second. And we'll have a long ladder that's 20 feet. So now to find dy dx, we need some relationship between y and x. But we have one. We have the Pythagorean relationship. We have y squared plus x squared equals 20 squared. Well, find dy dx, we can go, well, we could solve for y, or we could use implicit differentiation. It's kind of an easy choice. 2y, y prime equals 2x, plus 2x equals 0. So y prime equals negative 2x over 2y, with 2's canceled. Well, okay, so that tells me right away, since I need an x and a y, I'm going to need to know where the ladder is at some point. How fast this is moving is going to change with time. So you have to give some point. So let's say when y is at, say, 10 feet. So if y is 10, that's 100 plus x squared equals 400. So x will be equal to square root of 300. So we would plug in square root of 300, 10, and now that's our dy dx. And if we want to find out how fast x is moving, that's our dx dt. So we just have to divide negative 5 by this number. So that would be a typical related rates problem. The other common one would be something to do with a problem that kind of looks like this, where water is in a trough and it's dropping. The water is leaking out at some fixed rate. How fast is the top of the surface moving down? How fast is it going down? And since the geometry here is not, it's not a rectangle, it's not going to be a constant. So we need some kind of relationship of the volume to this rate here. Other problems where you're like blowing up a balloon, which has a volume of 4/3 pi r cubed, and maybe you're increasing the volume by some constant rate, and you want to know how fast the radius is changing. It's the same kind of thing. I think all these problems were on the homework, and you should probably review them just so you're familiar. Right. You're like, well, why didn't I just come in the first day and just do this day and take the final on the first day and be over with it? That wouldn't work, would it? Assignment homework. That wouldn't work. All right. Linear approximation. You have some function. We have its value at some point. and we want to estimate its value at some point x0, and we want to find its value at some other point, some little h from here, x0 plus h. This is some function. So we use a linear approximation. We approximate the function at this point by its linear equation. We don't have to go through, you could go through the whole process of finding m, finding the slope, and finding the equation of the line, and then finding out what this is, but we have a convenient equation to tell us. Right? It says that f of x plus h is the derivative at x. I'm going to get it wrong. It's f of x plus h times the derivative at x. I think that's right. So if I said, let's 8.001 cubed, think, well, f of x here is x cubed, and prime of x is 3x squared. So if I want to find f of 8.001, 8.000 plus 0.001, where this is h and this is x, that's going to be cubed root of 8 plus 0.001 times derivative. I'm going to say the cube root. We wanted the cube root. Is 1/3 x to the negative 2/3. Okay, that's what I wanted to do. And, okay, so the cube root of 8, nice easy number, that's 2, plus 0.01 times what? 1/3, 1 over x to the 2/3. Well, now I have to do a little calculation here. What's 1/3 over 0.01 to 2/3. Oh, I guess I could figure that out pretty easily too. Cube root of that will be 0.1, squared 0.01. So it's going to be about 2 plus 1 over 300. Right? And then you can either do this by hand or use a calculator. It's a linear approximation. It doesn't really make sense for a function we understand real well. But if you were doing some experiment, you were plotting points, and you have a numerical function that we could find the derivative of, then if you want to do some extrapolation, you can do that. All right. What are we doing here? All right. Anyone interested in architecture or I could imagine artwork, interested in building a dome like we have across the way. It's useful to know the hyperbolic functions, which are easily definable in terms of e to the x. Doing engineering, these come in handy because in some differential equations, these provide a real obvious solution to a number of such equations. And like the trig functions, we have definitions for hyperbolic tangent. This is sine h over cosine of h. And you should know that derivative of the sine of h is the cosine of h. You should be able to figure it out just by applying our rules here, and that the derivative of the cosine of h is the sine of h, negative introduced like the trig functions. I think I'm going to take a break for 5 minutes now, and then we'll come back and we'll go over stuff. Again, if you think of any questions, please bring them up. Yes. Zero. Oh, why don't we do that one? We'll just kind of jump ahead here. All right, so well, the easy problem is not this problem. It's 0 to 1 of 2x minus 1. So that would be x squared minus x from 0 to 1, or 0 minus 0. Well, to understand this problem, it might help to graph it. We have a function which is 0 at a half, and it has a slope of 2, or I guess 2 would be more like this, or negative 2. And we ask for the area under it. So you can see right away that it's not going to be 0, it's going to be something else. You could attack this just directly using geometry. We just have some triangles and you can figure it out that way. But let's do it the way we would do it with calculus. Since we know the function switches at 1/2, we could make this 2x minus 1 dx plus 1/2 1. X minus 1 dx. All right, let's compute these integrals. We already know the antiderivative, so x squared minus 1 from 0 to 1 plus, minus x. X squared minus x from 1/2 to, 0 to 1/2, 1/2 to 1. Absolute value of. All right, so what's this? This is 1/4 minus 1/2 minus 0. That's negative 1/4. And this is zero minus, again, 1/2 minus 1/4 minus 1/4. So here we end up with 1/4, and here we end up with 1/4. So we just get 1/2. I'm sorry, you were shaking your head this way. Did you say you did get it or you didn't?
I don't get it.
Okay. Let's do something different then. That's the same. Let's look at integral of the sine function from 0 to 2 pi, at the absolute value. So the sine function looks like this. So we're going to get positive and negative area. And these are going to, if I don't have the absolute value sign, I'm going to get 0. But if I apply the absolute value, it's going to look like this. And you're going to get 2 positives that are going to add together. So how do we do that calculation right? Well, we figure out where the function goes to 0. Well, this is 2 pi. This is pi. So this is going to go from 0 to pi, sine of x, dx, absolute value, plus integral from pi to 2 pi, sine of x, dx, absolute value.
It was the where does it go to 0, that mechanical piece of something.
I'm sorry, what was the question? Yes, this is the point where you have to break up the integral. Now, it could get more complicated. You could have, you know, to the fifth minus 4x cubed plus 3. I'm making this up. I don't know what that looks like. But you might have a function that, you know, goes like this. And you have some positive, negative, positive, negative. But you have to integrate between these pieces and add them all up as positive because of the absolute value. Oh, yeah. We'll come, you know, we're going to get in it.
Movie is movie. I grew up to like movie is movie. This is really good for us. Because that was she was supposed to be a teacher. This is my sister. She pulled off with that whole teacher. So we don't want to was a great teacher. No, I remember when I was thinking older.
Okay, are there any questions you'd like me to, something you want me to talk about right now, or? Yes.
Can you briefly go over the Squeeze Theorem?
Yes. I'm going to do two things. First, I'm going to point out that the Squeeze Theorem is a little bit obscure. Since Stuart's on the curriculum, if you're a math major, I think we have at least one math major in here now, you're going to come across this very important theorem. I don't usually say this, it won't be on the final, but nevertheless, what is it about? Sometimes you're trying to find the limit of something, some function that's not so obvious. Like an example might be squares. I don't know. How about 0? How about this? There we go. Yeah, it's like, what's that doing? I mean, the sine function is wiggling around. Oh, here we go, 1 over x. That's what I wanted. X is kind of, you know, as 1 over x gets close to 0, x gets large and sine starts wiggling around. And I don't know exactly. I guess it's going to go like this, so I probably want to do something like that. I don't know. Whatever it is, it's just not algebraically easy. It's not continuous, or it's a little aberrant. But maybe there's still a limit. So our strategy, we want to find some limit at some point. See, let's say we want to find a limit, and it's hard, but if we can find bounding functions, say a g function, an h function, and we know that g is always greater than or equal to f, which is always greater than or equal to h. We can see that algebraically, and these two functions have a limit, and it's the same. We've squeezed f in between them. That's the squeeze theorem. Again, a little obscure for Calc 1. You get into higher level math, analysis class, use the squeeze theorem all the time. It doesn't really, the type of functions you need it for are interesting to mathematicians. They don't really show up in physics or engineering very often.
So you find the limit, you find the limit for both g of x and h of x?
Yeah. If the limit of g of x is equal to the limit of h of x, x approaches some value. And since f of x is always between them, even though we don't know what it is at the limit, the limit gets squeezed there. The closer we get to x, well, these get close to some value, so this has to get close to that value. So it's mathematically, it's very important conceptually, but as I said, it won't be on the final. Or if I've gotten totally senile and it is on the final, I'll have to mark it right, no matter what. No, that's it. Okay. This is actually, as I recall, this isn't the only obscure strategy for finding limits. There are some other ones that we wouldn't even touch in this class, but come up later on in mathematics. I don't know. I know most of the students in the class they need this as a prereq. And the reason you need it as a prereq usually is because it comes into play in like, say, in physics or engineering. Computer science, maybe not so much. They're just trying to make sure you can handle some abstract stuff. But mathematics, once you get beyond calculus, it just turns into this. I mean, it's already I find calculus pretty cool, but it just turns into this beautiful, beautiful subject where we're studying things that nobody notices. No, people don't usually notice them. Mathematicians notice them. They're just obscure things about, it's not about the physical world, it's about like this abstract idea space. Things like, you know, there being an infinite number of points on a line. What does that mean? How can that be? I thought I was trying to introduce one of these ideas on Tuesday, where we showed that you can have this tube, and its volume is finite, but its surface area is somehow infinite. It just seems kind of peculiar, but you can do the math and you can see it for yourself. So this kind of fits in there. It's, what is, as you get close to zero, what's really happening to this function? It's kind of weird. All right. I'm not supposed to do new material here, and this isn't really new material, but I realize there may be some confusion in this symbol because we use it at least predominantly in two different ways, and actually we've used it in a third way here. So I wanted to discuss like what these things mean for just a second. Should be repetition. This guy here, this is what we call an indefinite integral, and it's equivalent to our antiderivative. And if we have some function f of x such that the derivative of f of x is equal to f of x, then this is our antiderivative plus some constant. Which is to say that this doesn't represent a function. It represents a family of functions. So, for example, if I have some function f of x, whose derivative is my small f of x, I can move this function up and down. I didn't do a very good job that time, but you get the idea. You can move it up and down, and the slopes, I'm sorry, I've got it backwards. This is f of x plus, I'm getting my own notation messed up here. I have some function and I look at the derivative and I move the function up and down, the derivative doesn't change. That's because the derivative of a constant, which is what I'm doing here, adding a constant is 0. So when I reverse things, what I get is some function which we could add some arbitrary constant. Now, that constant, we may be able to tie it down in a particular problem if we have some additional information. But again, indefinite integral family of functions. Here we have something a little more concrete. It's a definite integral. Again, if I have the function f of x, it's going to be f of b minus f of a. This is a number. Some value. It represents the area under the curve between these 2 points. Now you might say, well, wait a minute, we could have gotten f of x plus some constant c, let's call it 5, right? Well, then this is f of p plus 5 minus f of a plus 5. The 5s are going to cancel. So it doesn't, this constant doesn't really matter here. I'm going to digress for a second. I don't think it was anyone in this class, but I saw in some homework, someone I pushed too far. I got people all excited about the idea that there's a constant here. And someone did a homework problem and whatever. So, well, this is like 6 plus a constant. Now, with a definite integral, you get a definite number. It's not, it doesn't move up and down. It doesn't get a constant. All right, so these are the two main ways you're going to see this. You will definitely see them on the exam. Just in case it was a bit confusing, we've seen this form. We were talking about the fundamental theorem, the one that connects derivatives and areas. And this is a function. It's my f of x minus f of a. So I just want to distinguish this. It's not a definite integral, which is a number. It's got an x in it. It's a function. It's not a family of functions. I've tied it down. I've figured out what the constant is. So you might want to, this won't come up very often, but you do want to have a clear notion of that these are 3 different things here. I'll leave off like making things more complicated by putting an x squared here. I don't think that's a real important distinction for us to figure. All right. We did a whole section on using derivatives to understand what a graph might look like. Wish I had a paired example. Let's say I have some function x cubed minus 2x plus yeah. Can I come up with something? Let's see if this works out. And I know it's a 3rd degree, and you should know this from pre-calc that the end behavior is going to go off to infinity here and down below, and it's going to have at least one root. But from calculus, we can find the derivative. So 3x squared minus x plus 1. And where the derivative is 0, that's going to tell us where any local maximum or minimums are. So I could put this into the quadratic formula. This is probably not going to come out very well because I didn't really think about it. Gosh, it's going to. 4 plus or minus square root of 4, 6 is 1 and 2/3. So at 1, I don't know where this is going to go through the axis, but it's going to be 1, my scale is not going to work here. Here's 1, here's 2/3. So I know already there's a local, probably a local min at 1 and a local max at 2/3. And I can find a point of inflection, a point where here it's obviously concave up, here's concave down, and I can find the point where that switches by finding the second derivative. That would be 6x minus 4 equals 2/3. Is that possible? suppose, no, that's not possible. I made some mistake here. Well, we could get the computer up and running and graph it, but nevertheless, this is a point of inflection where the second derivative is 0. It's a point where the function goes from concave one way to concave another way. Right? Here it changes not its direction, but direction of the curvature. And in addition here, since we know these points, we can figure out using the first derivative test. We can pick either a point, in each of these intervals and see whether it's positive or negative, and that'll tell us whether it's increasing or decreasing. Clearly, from this minimum on, it's going to be increasing. From here to here, it's decreasing, and then, to this point, it's increasing. So you can use those factors from calculus to get the shape of a graph. Anything else you can pull out of that? I guess you should know that there's this idea that along with having a local, in this case a local minimum, it's also an absolute minimum. If I define a function but just on some interval, it might have local maxes and minimums, but its endpoints might also represent an absolute max or an absolute min. Should understand the distinction if asked. I guess most of the problems we've looked at, these are polynomial functions, but they don't have to be. They could be an exponential function or some composition of functions that are both have polynomials and trig and log functions and whatever. And you can apply the same rules. I'll mention in passing, we looked at two theorems. We looked at Rolle's theorem and the mean value theorem. And Rolle's theorem says you have some continuous function where there are 2 points that have the same y value, and therefore there's some third point where the derivative has to be 0. And similarly, the mean value theorem said that you have a continuous function and you have 2 points on it, on that interval, that there has to be some third point on the function with the same slope as the line between those 2 points. This is way too obscure to worry about on the final for Calc 1. If you go on in math and analysis, you'll need to know these theorems in a little more detail, but we covered them. We're on midterms, so that's sufficient. And then I guess I could say a little bit more about L'Hopital's rule, we mentioned already that you have the limit of some ratio where this goes to some indeterminate form. It could be 0 over 0, infinity over infinity, negative infinity over infinity. These are indeterminate forms, then you can apply L'Hopital's rule. In more obscure examples, you might have something like 1 to the 0, or 0 to the 0. Infinity minus infinity. And in these cases, in order to apply L'Hopital's rule, you're going to have to do some algebraic manipulation. Yes?
What's the difference between indeterminate and undefined?
Okay. So I have some function, 1 over x. It's not defined at 0, it's undefined at 0 because we can't divide by 0. These are in reference to a limit. We're not actually evaluating them at the limit. Limits never care about, the value. It can be undefined, right? Okay, the limit here as x approaches 1. It's undefined at 1. But this is also undefined at 1, right? This is an indeterminate form because the numerator is going to 0, the denominator is going to 0, and 0 over 0 is in other words, the limit gets close to 0 over 0.
Okay.
So we don't have an algebraic way. We can't just plug in the value, because we get 0 over 0, which is undefined. So these are just forms that a limit might approach, which we can, when we identify them, we can use L'Hopital's rule. So let me just try a different one. Well, this is too easy, but okay, so this limit as x approaches 1, this is going to infinity, this is going to infinity. At 1, it's undefined. I don't know what infinity over infinity is. But this function may approach some value.
So you don't use indeterminate when you're talking about limits. You don't say it's indeterminate when you talk about limits.
You don't really say, I think it's the opposite, you don't say undefined.
Okay.
At the limit, the function may be undefined, but we don't care, because that's not a problem for limits. The question is, what is it getting close to as it gets close? So once we identify one of these indeterminate forms, then we know we can apply, I guess I should write it. L'Hopital's rule. Now, what I wanted to get to is in the case of something like this, let's say limit is x approaches 0, x to the x. Well, okay, that's an indeterminate form. It's going to 0 to the 0, but there's no ratio here. So we have to do some work. We have to say, all right, that's f of x. I need to manipulate it in a way that I can get it into a ratio. So the way I do it is I find the log of f of x. It's the log of x to the x, which is now x times the log of x, which we could write as log of x over 1 over x. So now, as we get close to 0, log of x goes to negative infinity. 1 over x goes to infinity. It's one of our indeterminate forms. And we can find what the log approach is. And when we do that, then we have to reverse that to find what the function actually gets close to. Yeah, I can see the confusion between those terms, because if you were to evaluate a function and you get any of these, it is undefined, right?
It is over infinity undefined. And if you get something over infinity, just in a regular function, that undefined.
Well, if something approaches 1 over infinity, it's
Pretty screwed up.
yes, it is undefined, but the limit will be clearly 0, right?
Yeah.
In other words, if we have 1 over some function x, and x just keeps getting bigger and bigger and bigger, what do we get close to? We get close to 0. I guess this is a total aside. It's an important, usually confuses students. Infinity is not a number. It's not a number. It's an idea. It's like means we're getting bigger and bigger and bigger, but there's no, in most mathematics, there actually is obscure branches of mathematics where we define a value greater than any other value. And it doesn't sound real, and that's because mathematics isn't about reality, it's about ideas. But yeah, these are all undefined. These are all undefined. And they are indefinite forms that can be identified to be as something you can use L'Hopital's rule with. Anything on the exam will be much more down to earth than this discussion. I guess that's the way to put it. All right. I want to mention optimization problems briefly. I don't want to spend too much time because I really want to have some time to look at finding integrals. But basically, an optimization problem is a problem where let's see here. I guess the typical problem is we have, some rope. We want to put it in some shape. You might want to put it in the shape of a triangle, and the rope is going to be the perimeter, and we want to optimize, say, the area. If I want to minimize the area, I can just, have the rope go around here, and I can get an area of 0. It's not as obvious if I want to maximize the area. But basically, you need to develop an equation for the area, some function that describes the area in terms of this perimeter here, some length. And then you just use what we know about derivatives. You find the first derivative and you see where it's 0, and that tells you where the max and the min is. We've done quite a few problems. We've had them on exams, so I don't want to belabor that. I'd much rather spend a little more time talking about integrals. So along with we had a list here of derivatives. I'm just going to write representative here. I guess I should mention, since it's one of the more obscure but really important functions, the natural log function. Do recall that its derivative is 1 over x, please. So with each of these, we have kind of the reverse operation. Undo the derivative. We call that either the antiderivative, or we might call it indefinite integral. And, we can reverse this formula. We're using a different n, but this becomes x to the n minus 1. Here we're adding, x plus 1. Here we're subtracting 1 from n. Here we're adding, and we divide by n plus 1. We always write these with a constant because derivative of a constant is 0. You can add any constant you want and you can still get back. The rest of these are just kind of recognizing, if you can go forward, you can go back. And roll the cosine of x. Indefinite integral is going to be the sine of x. E to the x couldn't be easier. And it's good to know that integral 1 over x. I don't think you're going to trip over this. Technically, it's 1 over the absolute value of x. But you needn't worry about that detail too much. And just as we had a bunch of rules for finding derivatives, some of them just apply directly. Integral of x plus g of x. We can just find the integral separately. There's a sum. Well, I don't really need a constant because that's implied here. The one really useful pattern to look for is that if you have the derivative of a function over the function, that can be the log of the function. Now, let's just look at this. I want to find the derivative here. That's going to be 1 over f of x times the derivative of x. That's the chain rule. So finding this pattern is kind of finding the reverse of the chain rule in, when you're thinking of 1 over x, where x could be a function. Along with just looking at integrals and going, aha, I know how how to do the derivative backwards. This is just one of 2 important methods we've looked at to undo differentiation. The other one is, of course, the last thing we covered, substitution. Well, actually, a lot of these problems can be done with substitution, so let's say so how do we go about this? Well, we we managed to pick an appropriate substitution. Let's set u equal cosine of x plus 2. And find the derivative of u in terms of x. That's going to be negative sine of x dx. And we notice that sine of x dx is exactly what we have here. So we can substitute. This can become negative du over u, which of course is negative log of u, which substituting back becomes negative log of cosine of x plus 2. So you should be able to do this operation where you choose some substitution, try it out, right? Substitute and after you get an easier integral to do, substitute back. Any such problem on the exam would be pretty elementary. In Calc 2, if you move on, they will work you into some much more complex examples. And there's a number of other strategies for undoing integration that we will learn in that class, but not here. I think that's it. I mean, you also, again, bring your calculator if you have one. Use it for checking your work. Ask you to graph something. You can at least get a feel for what the graph ought to look like. And the calculus will tell you exactly where the points are if they're not obvious. I think that's it. Other questions? I can hang around here if people want to come up to the board, have any problems. Again, since not everybody is here, exams on Tuesday. I guess it's 10 o'clock. Is that right? Yeah, 10 o'clock. Bring the calculator if you have. Grab one. If you don't, I'll loan you one. Bring a cheat sheet, 2 sides. Good luck.